totally disordered. So for example, that's very complicated because there's no symmetry involved in the disorder overlay layer. The other one is that you have order overlay layer. In other words, you have periodicity. You can see periodicity in your overlayer, but and coherent with the substrate. What that means is that your 2D symmetry of your overlayer come in sync from time to time with the periodicity of your substrate. Okay? What does that mean? It means that let's say you have a grid like this. You have a grid like this. If you put your absorbing, here I draw a little CO molecule, if you like. I can draw a little CO molecule. If a CO molecule always occur in the bridge site, every other bridge site, then this is a coherent structure of my overlay with respect to substrate because all my substrate are in sync with respect to all my overlay structure are in sync with the substrate. However, if you have the overlay layer building its own crystallinity, right? It doesn't care about the 2D symmetry of your substrate. You just have a flat layer on top. Then you would have something order but in coherent structure. So a classic example of this will be ice, for example. Ice on anything. Ice is a very strong water itself has very strong intermolecular forces. So it just forms its own bond. It doesn't need to form bond in between, like with reference to the substrate grid that you have. Okay, so here you would say that ice would form an order structure because the ice itself is a crystal, right? And it has its own structure, and then you just need a cold surface to stay on it, right? So any cold surface, it really doesn't care about the crystal structure of the supporting substrate. So that's an example of an order but incoherent with respect to substrate, right? So it forms a nice order structure here, but there's no relative position that each of the overlay unit has to respond to this substrate unit. Okay, there's no correlation, in other words, of each of these with respect to this. Whereas in here, there's a correlation between the overlay and unit with respect to the substrate unit that you have. Okay, so we say here this order structure is very difficult to treat because it's not really crystallography, it's amorphous. Although there are new tools now that people are working on now to try to quantify an amorphous structure. So this order really is amorphous structure by looking at, for example, correlation length, right? So how nearest neighbor, for example, how many how many pairs of neighbor form a certain length, right? You can sort of correlate, do some correlation like this. It's still a very difficult field to look at amorphous material. Okay. You can look at broadness of your diffraction beam. For example, that's another way to characterize the disordered surface that you got. It's interesting because we are talking about amorphous, but hard to do. The other two cases, we can reference these, right? We can use our substrate grid as our reference, and then we can sort of identify them or classify them with reference to this substrate grid. And so I'll tell you a little bit how we can do this. First of all, by convention, we always say the substrate grid has one by one. It doesn't really matter what the actual surface structure we have for the substrate grid, because the substrate grid is if your substrate grid is a cubic or rectangle or hexagonal, unit cell, it doesn't matter. We always call that reference generically as a 1x1 structure. And then we then designate your overlayer with respect to this 1x1, so-called 1x1 structure. So 1x1 is like your ideal surface, and then we construct the surface with respect to this. Okay, we refer to overlay layers self-etch or absorbate. Right? Remember how we to this substrate mesh or the grid that we have. Okay, so quantitatively, I introduce a little bit of jargon here. If you take two vector B1, B2 to be the basis vector, if you like, of this overlay grid, right? So I would have, for example, in this little thing here, I would draw the blue dot to be my substrate grid, right? So and there are two vector. Let's say this is A1, this is A2, this sort of thing, and then I have my overlay layer, which is represented by my red. I call this one B1 and B2, right? Two axes, again like this. And by convention, also the ones are always the length in terms of the length is always smaller than the twos. So A1 will be less than A2, and B1 will be less than B2. That's the convention. So you always draw the smaller one, reference the smaller one first, and then if you have a rectangle, B2 will be bigger than B1. Okay. So we have these two sort of mesh, if you like, and now you can reference the red grid with respect to this blue grid, which is a substrate one that you have. So that's the logistic that one is trying to do. And the first one, first notation started in 1964 by Woods. Is a very simple one. We assume that this angle, right? So there's an angle formed between A1 and A2, an angle formed between B1 and B2. These two set of vectors. We assume these two angles are the same. Okay, but they don't need to be, right? Of course, we're just talking about a rather restricted class of overlay structure. If the grid happen to have the same mesh angle, then you can use the Wood notation. It's very transparent and it's very easy to use. That's why people are still using this Wood notation. Now, if this angle is the same, let's say they are 90 degrees for both the grid, the red grid and the green grid, then you can sort of find out, you can sort of use this, the difference in length in the direction. So B1 divided by A1, this vector divided by this vector, we call this M. We're looking at just the magnitude of these vectors. And similarly, you look at B2 versus A2, right, in the same direction. We call it N, right? And M and N are integer, right, in the Wood notation, which means that you're really looking at very restricted number of overlay structure, because they have to sort of fall into integral. In other words, your overlay grid has to be, the vector has to be an integer multiple of the substrate grid. Okay, so very restricted set of absorbing or overlay structure that you have. Okay, so both M and N are integer, and theta here, right? So even though the interangle of these are the same, there could be a rotation, right? So you can imagine the red grid rotated by 45 degrees, right? You can imagine that they rotate by 45 degrees. And that angle, that rotation angle, with respect to the original blue grid, is known as the theta angle, the angle of rotation required so that they can, in sync, they can go in the same way. Okay, so first of all, so these are very interesting, again, very restricted number of overlay structure that we can describe by Wood notation.